For our second set of notes for this class, we are looking at analyzing the graphs of functions. And these graphs are the typical two-dimensional Cartesian plane graphs that you're used to seeing. We're just going to start using the function notation to indicate that these graphs are a function of maybe time, or they're a function of some other variable that we wish to include in the domain of the function itself in consideration. So for the first thing we want to look at, for example 1, we're looking at this graph and we want to find the domain of the function. We want to find the function values at f of -1, f of 2, and then we also want to look at the range of the function. So when we're looking at a graph and we want to evaluate the domain, the first thing we're looking at here is the domain. The domain is the set of all x values upon which the function is defined. So if you look, when we're looking at the domain values, we're only looking at the x-axis. So the first point where this graph is defined is right here at -1. And then the graph is defined for every one of these x values all the way up till we get to 5. The graph doesn't extend beyond an x value of 5, and it doesn't extend in the negative direction beyond the x value of -1. So the domain is going to be all the x values from -1, and I wrote down 5, from -1 to 5. And if you were to write that in interval notation, you could write that as -1 to 5. Now, why are we putting the parentheses around the 5, and why did I put strictly less than next to the 5? It is because of this open circle here at that point 5, 2. The graph is not defined at 5. That open circle indicates that the x value of 5, that graph approaches 2, but the graph itself is not defined at 5. So when we're looking at the interval notation or the set notation for this particular graph for the domain, it's from -1 inclusive, but up to 5 not inclusive. So it does include -1, and then it goes all the way up to 5, but it doesn't include 5 itself. So that's why we indicate that with the parentheses or with the strictly less than symbol. For part B, we are looking at the function values at f of -1. So what that means is we just go to -1 on the x-axis and we go up to the y value on the graph. I don't know what I just did. There we go. We go up to the y value on the graph. That corresponding y value is +1. So f of -1 is equal to 1, because that generates that ordered pair -1, 1. X is the input, y is the output. For f of 2, do the same thing. We go to +2 on the x-axis. In this case, we go down to that y value, and it is -3, which corresponds to that ordered pair, +2, -3. And then finally, for part C, we're looking at the range. The domain looks at the x values, the range looks at the y values. So when we're evaluating a graph only for its domain or range, when we look at the range, we start at the lowest y value. So in this case, it's at -3. And then we go up to the greatest y value. And in this case, it is, I still can't get it right, +3. So we're looking vertically. So the range is going to be all the y values such that -3 is less than or equal to y, less than or equal to 3. Or you could say interval notation, -3, +3, square brackets around each of those, because of the closed circle at this -3 and the closed circle at this +3. So that's how you graphically determine a domain and range, or how you graphically evaluate a function at a given point. The vertical line test is a test that we can apply to a given graph to determine whether or not that graph represents a function. And if you read the definition here in the green box, it says it's a set of points in a coordinate plane is the graph of y as a function of x if and only if. That is the key word right there, or key phrase. If and only if no vertical line intersects the graph at no more than 1 point. So we're going to apply the vertical line test to these three graphs and determine whether or not the graph represents y as a function of x. So the first graph is the square root function. And if I draw a vertical line through here, it intersects at 2 points. So this is not the graph of a function. For the second graph, anywhere I draw a vertical line, it doesn't matter where that vertical line occurs, that graph will always be intersected at only 1 point. So yes, this is a function. And then for the third graph, anywhere I draw the line, it's not going to intersect at more than 1 point. And so we will say again that yes, this is a function. If you're curious why the third graph represents a function, because of this empty space that we have where this line doesn't intersect, all that simply means is that graph or that function itself is not defined between these two x values. It can still be a function, it just has a portion of the graph where it's undefined. So as long as the graph that does exist on the page or on your screen or whatever you're looking at is not intersected in more than one location by a vertical line, it can be a function. The next thing we want to look at are the zeros of a function. The zeros of a function occur whenever our function is equal to 0. And so all we have to do is just take the function, set it equal to 0, and simplify, and then we'll find out where the zeros of that function occur. Part A is an example of one where we're going to have to do some factoring, and I told you we would end up doing that plenty more times throughout this course. So here's a new example. So we just have 3x squared plus x minus 10. We've set that equal to 0. The way you factor a quadratic with a leading coefficient greater than 1 is we do factor by grouping. And to do factor by grouping, we would take the first coefficient, 3, multiply it by our constant, which is negative 10. So 3 times negative 10 is equal to negative 30. And then we look at our middle coefficient, which in this case is positive 1. But we are looking for factors of negative 30. In other words, two numbers that multiply to give me negative 30. But when I add those two numbers, they equal positive 1. Now, if you recall, again from the other day, when we were looking at these functions, and we were talking about factoring, if we look at the sign on the constant, in this case it's negative, that tells me that both of my factors have opposite signs. One's positive and one's negative. The middle term tells me which sign has the largest value. So my largest value will be positive, my smaller value will have to be negative. And when I think about factors of negative 30, the quickest one that comes to mind that I know has a difference of 1 is positive 6 times negative 5. 6 times negative 5 is negative 30. 6 plus negative 5 is positive 1. So I have found the factors that I want to work with. So the way you factor by grouping with a quadratic that has a leading coefficient other than 1, we start out, we write out the leading term, and that middle term, that positive x, we're going to rewrite it in terms of our two factors that we found. So it'll be plus 6x minus 5x. And then our constant remains the same, minus 10. If you notice these two middle terms, 6x minus 5x, simplifies to positive x. So we've not changed the value of the expression. We've just written it in a way that's going to make it easier for us to factor. So factor by grouping. We take the first two terms and the last two terms and group them together. If I look at the first two terms, 3x squared and 6x, I ask myself, what do they have in common? They both have 3x in common. So that means that 3x times x is 3x squared, and 3x times 2 is 6x. So this is the factored form of the first two terms. The next one is going to factor very similarly, but what we're hoping for is for the interior to end up being positive x and positive 2. So you have to ask yourself, what can I multiply x by and make it negative 5x? And what can I multiply 2 by and make it a negative 10? In both cases, the answer is negative 5. And the way we write this out now that we've come up with the factors, we have a repeated factor of x plus 2. And then what we're left with is the 3x minus 5. That is the factored form of our original quadratic. And then we apply the zero product property, which we discussed, I believe, on Friday. The zero product property just says if I take each factor, set it equal to 0, and solve for x, then I'll have my solutions for x. So the first one, I subtract 2 from both sides. And the second one, I add 5 to both sides, then divide by 3. And I have found my zeros of the function for part A. For part B, we're dealing with a radical. And when you're working with a radical, all you need to do is you need to take what's inside the radical itself, in this case 10 minus x squared, and set it equal to 0. And then when we simplify this, we solve this for x. So we would subtract 10 from both sides. And then we would divide both sides by negative 1. And then take the square root. When we take the square root of both sides, we end up with x is equal to plus or minus the square root of 10. And that's the zeros of that particular function. Then for part C, what we're looking at here, this is a radical, or not a radical, but a rational expression. And with a rational expression, all you're focused on is the numerator when you're looking for the zeros. So you just take the numerator, set it equal to 0, and solve for your variable. In this case, it's t. So we'll add 3 to both sides and divide by 2. And there's our 0 for part C. Increasing and decreasing functions. It sounds exactly like what you would think. We're looking at where the function is increasing, where it's decreasing, and where it might be constant. For example 4, we're going to use the graph to describe the increasing, decreasing, or constant behavior of each function. For this first graph, this is a cubic function, and it is always increasing. Even in this part right here where it looks like it's flat, if we continued to zoom in on that, you would see that it is still slightly increasing across that entire portion. So it is never constant. As we move from left to right on the x-axis, we see that this function is increasing across its entire domain. So this is increasing from negative infinity to positive infinity. Our second graph is not quite the same. It's increasing here and here. So we'll say from negative infinity, and this looks to be negative 1. We'll say that's negative 1, 2. That's what it looks like. And then this is positive 1, negative 2. So this is increasing from negative infinity to negative 1, and then again from 1 to positive infinity. Now it's decreasing in this middle portion right here, so it's decreasing -1, +1. Our third graph has all three properties. It's increasing on this interval, it's constant on this interval, and it's decreasing on this interval. So it's increasing from -infinity to 0. It's constant from 0 to 2, and then it's decreasing from 2 to infinity, because that graph is going to keep on extending on out as it goes. So that's how you determine the increasing, decreasing, or constant intervals of a given graph. One thing that the reason that is applicable is because we're going to look at something what's called the average rate of change. Later on, we're going to determine what's called the instantaneous rate of change when you take a calculus course. But right now, when we're just looking at intervals of increase, decrease, or constant, we can evaluate the function for several different values of x, kind of get a determination of where it's increasing, decreasing, or constant. But when we want to find precisely where that happens, we would have to apply calculus to that. We would have to apply derivatives. So right now, we're just going to focus on just trying to determine algebraically the best we can where a function is increasing, decreasing, or constant. Which introduces us to a new term, or two new terms. It's the relative maximum, relative minimum, or what I also sometimes refer to as the local maximum and the local minimum. And they are exactly like they sound as well. The one thing you have to remember, though, is that local maxes and local min values cannot occur at the endpoints of a graph. They can occur anywhere across the domain of the graph except at the endpoints. So if you look at this graph here in the middle of the screen, the endpoints are not included in the relative max, relative min, or local max, local min values, because for one, these two graphs both ends of it extend indefinitely in the negative and positive direction. So you can't make a determination on whether or not a relative max or relative min exists at any of those points. However, at a peak within the graph, you have a relative max. At a trough in the graph, you have a relative minimum value. So anywhere the graph is, I don't want to say below the x-axis, because you could have a graph that is completely above the x-axis, like this, and we have a max, have a relative max, and then here we have a relative min. But I think you get the idea visually where a relative max and a relative min would occur on a graph. And we're going to use a calculator here in example 5 to approximate the relative minimum value of the function that's given by 3x squared minus 4x minus 2. And for that, we're going to go to Desmos, and we're going to type in our function. Wish that would stop coming up like that. There we go. 3x squared. That's got to stop. Minus, okay. 4x. I don't know why this is doing this, guys. I apologize. 4x minus 2. Okay, so there's our graph of 3x squared minus 4x minus 2. Now again, Desmos.com is a free online graphing calculator. It'll make your life really easy for right now until we can get you guys an Inspire. But you can see on the graph right here is the lowest point of the graph, and that's going to be that relative minimum value. And what's nice about Desmos is if you click on that, it gives you the x and y coordinate of that specific point. So here, when x is 0.667, which is also 2/3, the corresponding y value is -3 1/3. So all we had to do for that one was use a calculator. And the relative minimum value is -3 1/3 at x equals 2/3. If you want to put the decimal approximation, you can. Here's where we introduce the average rate of change and what we call a secant line. So the average rate of change is very easy to calculate. It's basically the slope formula. Again, if you wanted to be more precise, we would have to apply derivatives, and we would have to use calculus to come up with the instantaneous rate of change. But let's just say, for example, in this generic graph, we are looking for what is the average rate of change from this first point that we're going to call x sub 1 to the second point, which is x sub 2. The way we compute that is we evaluate the function at x sub 2, and then we evaluate at x sub 1, and we subtract those two from each other, divided by the difference between the x coordinates. So that's just like the slope formula that you've seen before. We're just introducing a new notation by adding this function notation in the numerator. And example 6 should make it pretty clear what we're looking at. So for example 6, find the average rates of change of f of x equals x cubed minus 3x from negative 2 to 0. So for part A, the first thing we want to do is evaluate the function at negative 2. And then we simplify. Negative 2 cubed is negative 8. Negative 3 times negative 2 is positive 6. And we get negative 2. We also need to evaluate it at 0. And that's just going to be 0. So what we want to do now is, if I label these, that's x sub 1 and that's x sub 2. If we go back to the notation, it's f of x sub 2 minus f of x sub 1 over x sub 2 minus x sub 1. So our f of x sub 2 is this value right here, 0, minus f of x sub 1, which is negative 2, over our x sub 1 value of 0 minus our x sub 2 value of negative 2. And when we simplify that, we get 2 over 2, which equals 1. So the slope of our secant line from negative 2 to 0 is going to be 1. We can do the same thing for part B, where we are calculating the average rate of change from 0 to 1. So again, we're going to evaluate our points at f of 0. It's going to be 0 cubed minus 3 times 0, which is 0. And then we evaluate f of 1, which is 1 cubed minus 3 times 1. So we get 1 minus 3 is negative 2. So now we're going to use the average rate of change formula. And so f of x sub 2 is negative 2 minus f of x sub 1, which is 0. So that's the negative 2, and there's the 0. And then it's going to be divided by our x sub 2 minus x sub 1. And we get negative 2 over 1 is negative 2. So the average rate of change from 0 to 1 is negative 2. And we can apply that here on example 7. It's a similar question. We're talking about the stopping function of a car, and it's given by the equation s of t is equal to 20t to the 3/2 power, where t is the time in seconds. Find the average speed of the car from 0 to 4 seconds, and then from 4 to 9 seconds. For part A, we're going to look at s of 0 is going to be equal to 20 times 0 to 3/2 power, which is just going to be 0. Then we look at s of 4, which is 20 times 4 to the 3/2 power. And the 3/2 power is the same as the square root of that value cubed. We'll look at fractional exponents later on in this class. But for right now, it just simply means the square root. In this case, that tells me it's the square root of 4 cubed. So that would give me 20 times 8, which is 160. And you can verify that by typing in a calculator. So then when we look at this, we get s of 4 minus s of 2, s of 0, over 4 minus 0, When we simplify or substitute in what we know, S of 4 is 0. S of 2 is, S of 4 is 160. S of 0 is 0. Over 4 minus 0. That's 160 over 4, which is 40. So the average speed of this car from 0 to 4 seconds is 40 feet per second. Because our distance is given in feet and our time is in seconds. So it's 40 feet per second. For part B, we're going to evaluate S of 4. So that's going to be, again, 20 times 4 to the 3/2 power. We've already computed that once, which is 160. And then we look at S of 9, which is going to be 20 times 9 to the 3/2 power. Let's see, that's going to be 729. And then the square root of 729. Sorry, I don't remember that one off the top of my head. But I hate the way that keeps popping up. So it's the square root of 729. Oh, it's killing me. Is 27. So S of 9 is equal to 27. So again, we're going to substitute those values into the average rate of change formula. And we get 27 minus 160 over 9 minus 4. 27 minus 160 is negative 133. 9 minus 4 is 5. And then when we divide those out and get a decimal approximation, we have negative 133 divided by 5. And I need to fix that. So it's going to be negative 26.6. And you may wonder, okay, how did you get a negative rate of speed? That car is decelerating as it goes from 4 seconds to 9 seconds. So it's moving towards the stoplight. At 0 seconds to 4 seconds, its speed is increasing, or it's at 40 feet per second. But then as it starts to decelerate, its speed or its velocity becomes negative 26.6 feet per second. It's slowing down as it approaches the stoplight. And our last example, we're looking at even and odd functions. The way we determine whether a function is even or odd is simply evaluate the function at negative x. So a function is even if we evaluate it at negative x, we get the original function back. It's odd if we get an opposite function back. And we'll see that in these two examples. So for part A, if I evaluate this at negative x, I simply replace x with negative x, and I simplify to see what happens. So negative x cubed is negative x cubed minus a negative x becomes plus x. If you'll pay attention to the signs here, negative and positive, this is positive and this is negative, each sign is opposite of what we started with. So this is the opposite function of what we began with. This is an odd function. For the second example, we're going to do the same thing. We evaluated at negative x. And when we simplify that, we get x squared plus 1. That is the exact same function we started with. So it is even. If you happen to do this process and you get some signs change and some of them don't, so it's neither even nor odd, you just simply state that that function is neither even nor odd. But in this case, we ended up with an odd function for part A and an even function for part B. I'm sure that this will probably lead to a few questions, so just ask me those questions. If we want to discuss them tomorrow, we can, or we can wait till Wednesday. Remember, we're going to meet Monday, Wednesday, Friday for sure. Tuesdays and Thursdays will be strictly optional. So I hope everybody has a great evening. I'm sorry this took so long to get out to you. There's been some internet issues. That's the worst thing to happen during this time, but that's what happened. So that's what we got to deal with. I hope everybody has a great night, and I'll be talking to you soon.